This is an introduction to the intermediate lab experiment called SLM, or Spatial Light Modulator, Amplitude Modulation. In this video, you'll get background on what a spatial light modulator is, how you're going to use the equipment, and a little bit of the theory of phase and amplitude modulation. So the student learning outcomes for the lab are to learn what the alignment axis of the spatial light modulator is, and what that means. What is the alignment axis? And also to understand the principles of amplitude modulation using a phase-changing SLM. The lab objectives means what will you do during this lab? In other words, what will you get by the end? What will you know and report in your lab notebook by the end of the lab? In this lab, they are 1, to find the alignment angle of the SLM, 2, calibrate a conversion for this SLM from pixel grayscale to phase change. So you will know how to program it, and this is 3. From your calibration information, you could figure out what the grayscale or pixel level is for a particular phase change of light. There's a lot of new words in that introduction, or in the objective. So let's start with something pretty basic. What is a laser? Many of you know that laser stands for light amplification by stimulated emission of radiation, or LASER. Just skip the B and the O. And there are particularly important features of a laser. That includes that it's monochromatic, which means it has one color, a very narrow bandwidth of color. It's collimated, more or less. You'll see in the Gaussian beams experiment that it's really not collimated, which means that it travels as a narrow beam. So the definition of collimated is that it will keep traveling along the table, around the room as a narrow beam of light. It's polarized, which means it has a defined electric field direction. That's true of our lasers. And the laser has a particular mode, which is a defined intensity profile of the beam. The laser you will use for this lab has a Gaussian mode profile. So let's step back and learn some information about the things we've just talked about. What is polarization? Very short description is that since light is an electromagnetic wave, so it travels with an electric field and a magnetic field, the polarization of the light refers to the direction of the electric field of the light. So this schematic shows an electric field oscillating up and down, the red lines, and a magnetic field perpendicular to that, side to side, the blue lines. We're going to ignore the magnetic field and just pay attention to the direction of the electric field. And that is the polarization of the light. Some examples of polarization. A linearly polarized wave is the one on the left here. The linear polarization means that the electric field vector is simply going up and down. So the black arrow on the right hand red bar is going up and down. As the electric field passes that red bar, it is either up or down. So we call this linearly polarized. The electric field vector travels only along a line, up and down in this case. You could have vertically polarized light, horizontally polarized light, diagonally polarized light, at any angle, and all of that would be linearly polarized. The GIF on the right is a circularly polarized wave. If you look at the black arrow on the right-hand side of the GIF, you'll see that it's traveling in a circle. And what it is showing you is it is tracing out the electric field as it passes that red axis. The electric field in this case is traveling in a circle. We'll talk more about circularly polarized light at another time. Now, what is phase? An electric field might be given by an equation or an expression like this, where you have psi of r, your position vector, and t, is equal to some amplitude, a, that's a function of the position, and a phase term. This is an exponential term, e to the I k dot r minus omega t plus phi, where this term oscillates because it's an exponential, because it's an imaginary exponential, that I part. It oscillates in space and in time. So the phase of the field is the oscillating term. It shows how the wave changes with time and position. The phase in this case would be the term in the exponent k dot r minus omega t plus phi. What does that mean for us physically? If the phase is the oscillating term, what it means is we can look at this blue electric field traveling down in the right-hand corner now, and we can say, is it at a maximum or a minimum or anywhere else? The phase is going to be where it is in the cycle, in a full wave cycle of the wave. So at some instant in time, that black arrow will be pointing either up or down or be zero, and those are all different phases of the wave. And they're given by that phase term. Now, a spatial light modulator, or SLM, is a device that modulates the spatial distribution of light waves. Okay, so spatial distribution means you look at a laser beam, which of course you're not going to do, coming straight at you, and it has a shape, a mode. It looks like a circle, say, coming towards you. And we can change, using the spatial light modulator, we can change parts of that mode. It does this by changing the phase, this is why we've talked about phase, of the cross-section of the beam. That's the part of the beam that's coming towards you. And the SLM is broken up into pixels, so it'll change each pixel of the wave, depending on how you program it. For us, what will happen is when we change the phase, the appearance of the light will change. So that means either it'll get brighter or dimmer. Usually it changes its mode. So how it looks to us on a card or on a camera will change based on the change in the phase. This particular SLM is an LCOS SLM, which stands for liquid crystal on silicon, and this is a reflective type SLM. All right, so we'll come back more to equipment, but I'm just going to touch on the SLM user interface here as well. And when you open up the user interface, it won't have this same output pattern, but it'll have these 4 regions. The upper left region shows the output pattern of the SLM. So what is being sent to the little SLM active area. The upper right-hand corner is your control area. So in the top left here, you can choose the function item. You can choose, in this case, whether you're doing a beam shifting or a static Michelson or something else. We are not doing a Michelson interferometer experiment with this SLM. And this drop-down will be useful. This one that currently says Michelson interferometer is where you select an experiment. In our case, we will select amplitude modulation. You'll have parameters that you can change. Whatever is appropriate for that particular experiment will show up there. And in the bottom right corner, you have an experimental layout. Our experiment may not look exactly like that. It's a suggested experimental layout. What you're going to do is you'll click Generate and then Send to LCOS panel as you initially run the experiment, and that will send whatever is in the upper left to your LCOS or your SLM panel. All right, so each grayscale value, what you're going to do is program the grayscale value of each pixel, and it corresponds to a particular phase change. The grayscale goes from 0 to 255, and our SLM does a phase change from approximately 0 to 2 pi. So, I'll go back to that. So you can already make a guess about grayscale values to phase. knowing that grayscale goes from 0 to 255 and the phase will go from 0 to 2 pi. But we don't know yet what the precise correspondence is between grayscale values and phase. I want to give you a little idea of what happens when you change the phase of the light. So when you change the phase, one example of changing phase is something called a half-wave plate. Those who have taken optics are familiar with the half-wave plate. The half-wave plate is used to rotate the polarization direction of linearly polarized light. The way it does this is by creating a phase change between two orthogonal polarization components, and that phase change, delta phi, equals pi. It's called a half-wave plate because a pi phase change refers to half of a wave cycle, and so that's a lambda over 2 change. This picture down here, the red line shows the direction of the electric field, and the two blue lines are x and y components, basically any two orthogonal components that we can imagine breaking up our red field vector into. With a half-wave plate, the important thing for you to know is that the polarization direction of the light is rotated by 2 times theta, where theta is the angle between the polarization of the light and the axis of the polarizer, the axis of the half-wave plate. So let me clarify that. The polarization direction of the light is this red light. The angle between it and the axis of the wave plate would be, say, the green line or the blue line. So either the green or the blue, depending on how it's labeled. In this case, it looks as though theta is 45 degrees. And that means that our polarization direction would change by 90, or 2 times 45. So in general, we know that delta theta, the change in the polarization direction of our light, is equal to 2 times the angle between the polarization of the light and the axis of the half-wave plate. So in this picture, it's showing a phase rotation, or polarization rotation from 45 degrees to minus 45 degrees. So here the red light is at 45 degrees. As it travels through a half-wave plate, it rotates and comes out the other side at minus 45 degrees. In our experiment, we're going to adjust the angles of a half-wave plate and also an analyzing polarizer, which we'll call an analyzer. And we'll use that to convert the spatial light modulator into an amplitude modulator or a phase modulator. We'll be focusing on the amplitude modulation here. So I'm going to talk through how the SLM can change the phase of one polarization component and how that rotates the linear polarization of the light, and it will sound exactly like what I just said with the half-wave plate. Suppose that your electric field vector, your polarization of your light, is along this red line. And suppose that the spatial light modulator alignment axis is vertical. At this point, if this is the alignment axis, then the phase of the blue part of the light, the blue component of the light, could be changed. And the dotted blue component, and the solid blue component is not going to change. So we're going to use the SLM to change the phase of this dotted blue component. What that will become is a phase, your electric field pointing in a different direction, depending on how much you changed the phase of the SLM. So the outgoing light will have some particular polarization direction depending on the particular phase change of the component that lies along the alignment axis. So when we do this phase to polarization experiment and as an amplitude modulator, the the layout that you're going to see in the SLM control is something like this. We won't be using exactly the same setup. For example, we will have, instead of a polarizer here, we will have a half wave plate, and you also won't see the lenses in place. We don't need a collimating lens, and we won't use a focusing lens. In this section, you will now watch a live video about the equipment in the lab. This is your introduction to the equipment for the Spatial Light Modulator Lab, where we're going to do amplitude modulation, which will also have us learn about phase modulation. So I'm going to point out what you'll do, what the pieces are, and you will explore what you'll actually need to do for this experiment. First thing you want to do with any laser experiment is figure out where the beam is. So same with the Gaussian beams lab. Grab a white card, and you'll be able to see this, to trace the beam from where it starts, which is off the screen. Pick it up where you can see it. Right? So we can see a red dot on the card here. And let's jump through this little optic here. Here's our red dot. It's going to reflect off of a mirror, then go through this optic and through another optic to our spatial light modulator and reflect back. So you will do this first, explore where the beam is going. Now let me tell you what's here. This box is our spatial light modulator. So the box is labeled Jasper Display, and this is your SLM. It's connected to a display window, a display screen here. This is very delicate. Do not touch it, do not spit on it, or wipe your fingers around on this display. It's mounted onto a post. We won't need to adjust that, most likely. In front of the spatial light modulator is a cube, and the cube is a beam splitter. Use your card to explore what's happening with the beam splitter and where the different reflections are going. Before the beam splitter is an optic in a rotating mount. This is a half wave plate, which some of you have heard about and some of you have not. The half wave plate is going to be how we set our polarization of the light. We will leave it at 0 for this experiment. Before the half wave plate is a mirror. And we said the mirror simply reflects light from down the table towards the SLM. Now when the beam reflects off of the beam splitter, we have a component that's reflecting this way off of the beam splitter, and it's going towards a polarizer. This is a polarizer, it's a linear polarizer, and it will only pass the polarization of light along the 0 axis. Right now, I seem to have it at 90, which means the 0 axis is actually like this. It will only pass light that is along this axis. Okay, a couple things you need to know now that we've just mentioned polarization is that the incident polarization of the light is vertical, and this will let vertical light go to the SLM. And again, this is set right now, so it's at 90 degrees from vertical or horizontal. You can experiment with that as you go on. This is how we want it for this setup. The wave plate at 0, the polarizer at 90. What you're going to do is use the computer and a power meter. The power meter head is right here, and the power meter controller is underneath the computer, so you can't see it right now. You're going to use the spatial light modulator control and the power meter to adjust the amount of light that you see going to this card through the polarizer, and then you'll be figuring out why that amount of light is changing. The way we do that is on our computer, you'll have instructions on how to start this program. When we change the pixel level, when we change the gray level of each pixel in the little spatial light modulator, it will change the amount of light that goes through the polarizer, that actually makes it through the polarizer. Right now it's fairly dim, and we can change it and see that it gets brighter. Look at that dot now, it's a bit brighter. Change it more, see that it gets dimmer. Dot now is fairly dim. That's the data you're going to be collecting, is looking at the power on a power meter here, which again will be displayed underneath where this camera is, and looking at the gray level on the program running the spatial light modulator. And then get to figure out what's going on and why the amplitude is being controlled. If you have time, you'll explore with other variations on that control. And that's all. Your pre-lab questions you will write in your lab notebook. The two questions are, what purposes could you think of for an SLM? And what would a possible graph be of phase change versus the programmed grayscale value? So plot or graph a possible phase change versus grayscale value in your lab notebook for the pre-lab questions. As you get started, what you'll first want to do is sketch the experimental setup in the lab and talk about it with your group. Think about how you want to actually conduct the experiment, experiment a bit with the equipment, and keep safety considerations as a top priority. So the main safety considerations are to keep the laser beam at the same level in the lab. In other words, don't put mirrors in the beam such that the laser level goes up or basically up. And also, don't bump things, the laser, mirrors, or any other optics on the table unless you were doing it intentionally to control the laser. Enjoy the lab.